Hi everyone, welcome back to the part 3 of metallic bond. So in this part 3, we will be discussing on the band theory of metal. Alright, so metals are described as having luster, good thermal and also electrical conductivity, and are very malleable. So these properties are direct results of the ability of the atoms to contribute electrons to a common cloud around the atoms. So these facts indicate that the bonding in most metals is both strong and also non-directional. So the mobile electrons can conduct electricity and also heat by using the by the helping from the electron C. Okay, so let's go to the band theory of metals. So have you ever heard about molecular orbital? Okay, so in this band theory of metal, this is a bit where we have a relationship between a molecular orbital that will form what we call two wide space molecular orbital energy. We call it as a bonding and also anti-bonding. Right, then, okay, before that, you will learn more on the molecular orbital during CHM 579 Advanced Inorganic Chemistry. Alright, so I'll just introduce to you what is actually molecular orbital. Alright, so when this form, the bonding and also anti-bonding form, you know that in a piece of metal, of course we have many metal atoms, right? So these many metal atoms, when they interact, so a large number of resulting molecular orbitals become more closely spaced. Okay, when we have plenty of metal atoms interact, so we will be having more bonding and also anti-bonding orbital. So what happened here, they will finally form a virtual continuum of levels. We call it as bands. Okay, so in this diagram, okay, we have at the lower side or at the lower energy, we have a bonding. All right, in between bonding, we have the non-bonding. All right, and then we also have at the high energy level, we have anti-bonding. So you will learn more on the formation of sigma star, pi, and also pi star in molecular orbital later. Okay, alright, so let's say, okay, I have one example here, magnesium. Okay, let's say you have a small piece of magnesium. Okay, alright, it has a large number of atoms, usually around 10 to the power of 20 atoms. Okay, so when we have a 10 to the power of 20 atoms, so what happened here, it will form much more molecular orbital. It will form more molecular orbital bonding and also anti-bonding. So, and you know that the electron configuration for magnesium is actually ends, okay, at 3s2. Okay, so let's write the electron configuration for magnesium. Magnesium, we have a 12 proton number, so we have 1s2, okay, 2s2, right, 2p6 and 3s2, right. Sorry for my handwriting. Okay, it's so bad, right? Okay, then here, okay, after the 3s2, we are going to have the 3p. Okay, so this one will be the 3p0. Okay, all right. So each magnesium atom has a 2 valence electron here, okay, at 3s orbitals, and the 3p orbitals are empty. So this is the 3p0. So when many of these orbitals interact, okay, these orbitals, okay, these orbitals are referring to the 3s and also the 3p. Okay, when these two orbitals interact, there will be two types of bands can be formed. Alright, so the first one is the valence band, and the second one is the conduction band. Okay, the first one, what is actually a valence band? Okay, valence band is actually energy levels filled with the electrons. In this case, for the magnesium, this band is made up from the 3s orbitals. Alright, then second one is the conduction band. Okay, this is where we have the empty energy levels. For magnesium, the 3p will be the conduction band. Okay, then so this is a diagram that show you the 3s and also the 3p. Okay, why we are focusing on the 3s? Because you know that the valence electron for the magnesium are actually located in the 3s. Okay, so we have the two electrons here in the 3s and also empty 3p orbital. Okay, alright. So what happened here in these 3s, so the bonding and also the anti-bonding usually will be full. So, okay, what happened here, okay, if you look at this diagram, okay, the 3s and the 3p is overlapping, okay, right, these two bands are overlapping, so there will be no gap between the 3s and also 3p. Okay, when this happens, so what happened here, okay, magnesium will be formed, or magnesium can form as a conductor, can be a conductor because there is no gap. So it means that we have a positive charge here, and also the electrons at the 3p. Okay, alright, so when this positive, it means that it releases minimum of 1 electron. Okay, so we have the positive and the valence electron here, or the delocalized electron here. So what happened here, the transfer is so smooth, okay, and there is no gap, and this magnesium can be considered as a conductor. Okay, then alright, so in the band theory of metals, okay, also there are three categories of materials that may be easily understood by the energy gap, okay, between the bonding bands and the anti-bonding bands. Okay, the gap that we are talking here is this one. Alright, whether we have the gap or not. Alright, then so if there is a large gap in energy, okay, the material is called insulator. If the gap is finite but small, the material we call it as semiconductor. And if there is effectively no gap between the bands, this material are called conductors. Okay, so as you know, conductors are usually made from the mostly metals. Okay, insulators mostly from non-metal materials, while for the semiconductors are usually made from metalloids. Alright, so these are the gaps that we are talking just now. Okay, if you have a bigger band gap between bonding and anti-bonding, okay, alright, for example, let's say magnesium. Magnesium cannot be as insulator. Okay, so sorry about that. Okay, let's say if you have a big gap, okay, big band gap between bonding and anti-bonding, so this one will be considered as insulator. If the band gap is smaller than the insulator, this one we call as semiconductor. Alright, and then if we have no gap between valence band and conduction band, this is where we can call it as conductor. Alright, so by having this gap, okay, the difference in gap will give you a different materials. Okay, alright. Okay, then so we have what is the difference between semiconductor and insulator, because both of these having band gap here. Alright, so let's look at the difference between semiconductor and insulator. Okay, so both of these is due to the size of band gaps. Okay, if you have a smaller energy gap okay, less than 3 electron volt at 400 nanometer, this one can be considered as semiconductor. And if you have more than the large energy gap here, more than 3 electron volt at 400 nanometer, so this one can be considered as insulator. Alright, so I have another example here, which is calcium. Okay, so calcium should have a full 4s band, okay, and also an empty 4p band. So if they do not overlap, calcium would not be a semiconductor or insulator. But as you know, calcium is a metal, right? So this is because, okay, we have overlapping of 4s and also 4b in terms of energy. Alright, then this is what we have, where we have the valence band and also the conduction band. Okay, so this is where we have the field levels and also empty levels, okay, the 3s, the 4s, and also the 3p and also 4p. So when we add energy, okay, it will form a cation here and release one valence electron. Okay, so when this happens, the metal itself can conduct electricity. Right. But okay, metal conductivity actually decreases with increase in temperature. Okay, so this is actually contrary to expectation, because we would expect that when we increase the temperature, it will increase the electron promotion, right? But the ability of the electron to travel smoothly through the solid in the conduction band depends on the uniformity of atom arrangement. So when an atom vibrating vigorously at the side, so it's actually equivalent to an impurity. We call it as impurity that disrupt the orbitals. Okay, so that's why when we have higher temperature, means it will give you lower conductivity. I end our discussion on the band theory of metal and also the electrical conductivity here. So I'll see you in part 4, where we will be discussing more on the semiconductor. Bye!